The interaction of photonic crystals with variables such as light, photonic behavior, and plasma dynamics, including magnetohydrodynamic plasmas, can significantly influence the performance and behavior of a photonic crystal radion array. Let's break down how different aspects of light and plasma could impact such an array. 1. Photonic behavior in a crystal array. A photonic crystal is a periodic optical nanostructure that affects the motion of photons in much the same way that the periodic potential in a semiconductor crystal affects electrons. Photonic crystal radion arrays manipulate light to create band gaps, ranges of light frequencies where photons cannot propagate. This control over light propagation is critical for applications such as optical filtering, waveguiding, and photonic integrated circuits. Variables of light impacting the array. Wavelength and frequency. The wavelength or frequency of the light interacting with a photonic crystal array directly influences how the array behaves. Since photonic crystals create photonic band gaps based on their periodic structure, different wavelengths will be either allowed to pass through or reflected, depending on the crystal's design. A mismatch between the wavelength of the incident light and the design of the crystal can result in inefficient transmission or reflection. Conversely, fine-tuning the periodic structure of the photonic crystal can optimize the array for specific wavelengths. Angle of incidence. The angle at which light enters the photonic crystal also affects how the array manipulates it. Photons entering the crystal at certain angles might experience more or less diffraction based on the crystal's periodicity, potentially altering the array's efficiency in bending or reflecting light. Radion arrays designed for specific angular interactions can leverage this to direct light for beam steering or precise control of optical signals. Polarization. The polarization of light, whether it's linear, circular, or elliptical, can alter its interaction with a photonic crystal. Depending on the crystal's structure, polarization-sensitive effects might enhance or reduce the crystal's efficiency in controlling the propagation of light. Polarization-specific designs could improve performance in photonic crystal radion arrays, especially in applications like optical communications where polarization multiplexing is used. 2. Magnetohydrodynamic MHD plasma influence. Magnetohydrodynamic MHD plasmas, being ionized gases affected by electromagnetic fields, can have profound effects on the photonic crystal array in several ways. Plasma variables impacting the array. Plasma-induced refractive index modulation. Plasmas can alter the local refractive index of a medium when they interact with it. In the presence of a plasma, the effective refractive index of the environment around or within the photonic crystal array can change, potentially shifting the photonic band gap or altering the propagation characteristics of light within the crystal. This could result in dynamic changes to how the photonic crystal array transmits or reflects light, especially if the plasma's properties, density, magnetic field strength are variable. Plasma frequency. In a plasma, the plasma frequency determines how it interacts with electromagnetic waves. For a given photonic crystal radion array, if the plasma frequency is comparable to the frequency of the light being manipulated by the crystal, plasma oscillations could interfere with the transmission or reflection of light through the crystal. This interference could create dynamic effects, such as resonant absorption or reflection, which might be leveraged in tunable devices but could also lead to unwanted loss in efficiency. Magnetic field interactions. MHD plasmas are heavily influenced by magnetic fields, which can cause the charged particles in the plasma to move in specific patterns. This, in turn, creates secondary electromagnetic fields that can interact with the light passing through the photonic crystal array. Depending on the strength and configuration of these fields, they could either enhance or disrupt the array's ability to control light. This could lead to phenomena such as Faraday rotation, where the polarization of light is rotated as it passes through the plasma in the presence of a magnetic field. Such effects could either be a source of signal loss or be exploited for specific polarization control applications. 3. Combined photonic and plasma effects on a photonic crystal radion array. When photonic crystals are used in environments with magnetohydrodynamic plasmas, there can be a rich interplay of effects. For instance, dynamic tuning of the photonic band gap. By introducing a plasma near or within a photonic crystal radion array, the refractive index modulation caused by the plasma could allow dynamic control over the photonic band gap. In other words, the plasma's properties could be used to switch the crystal between different states, such as reflective or transparent for certain wavelengths. This capability would be especially useful in reconfigurable optical systems, where adaptive control of light is required. Plasma shielding. Plasmas can act as shields for certain electromagnetic waves, depending on their plasma frequency. If the photonic crystal radion array operates in a plasma environment where the plasma frequency is close to the light frequency, the plasma might absorb or reflect significant amounts of the incoming light. This could reduce the array's efficiency or create unintended losses. On the other hand, this could be exploited in optical filtering applications, where the plasma acts as a selective barrier for unwanted frequencies. Plasma instabilities and turbulence. Plasmas are often subject to instabilities and turbulence, especially in magnetically confined environments. These fluctuations in plasma density and magnetic field strength could introduce variability into the way the photonic crystal array interacts with light, potentially causing unpredictable shifts in the transmission or reflection properties of the array. If controlled, these instabilities might enable nonlinear optical effects within the array, but uncontrolled turbulence could degrade performance. Summary of impact on photonic crystal radion array. Photonic behavior, such as wavelength, polarization, and angle of incidence influences the efficiency and precision of light manipulation within the array. MHD plasma effects, such as refractive index modulation, plasma frequency interactions, and magnetic field dynamics, can dynamically alter the array's properties, potentially enabling tunable optical features but also introducing complexities like absorption or interference. The combination of these effects can either enhance the functionality of the photonic crystal array for applications such as dynamic filtering and beam steering or cause challenges like signal loss and turbulence. Induced disruptions.